Chapter 2 is all about differentiation, finding the derivative of a function. Section 2.1 is on the limit definition of a derivative. So we will define what a derivative is. We'll take a look at the notation of a derivative. We will look at how to find a derivative by using a limit process. And then we will look at a couple different rules on finding derivatives. So first of all, a derivative is the rate at which a function changes. The rate of change of a function, which sounds very similar to the definition of a slope of a line, the rate of change of a function. So a line does have a rate of change because it is in a straight line, and that rate of change is constant. The rate of change is the same at every point on the line. We call it a slope. A curve also has a rate of change, but for a curve, the rate of change changes. So here I have a positive rate of change. The curve is going up. At this point right here, I still have a positive rate of change, but it's not going up as quickly as it is at that first point. At this point right here, my curve is neither going up nor down, has a zero rate of change, and then it's negative and more negative and less negative and zero and positive again and more positive. So the rate of change of the curve itself changes at various points. The rate of change, the derivative, is equal to, if I were to sketch in a tangent line, remember, is a line that just touches the graph once. So if I sketch in a tangent line where it just touches the graph right at that point, the rate of change of the curve, the derivative, is equal to the slope of the tangent line. The slope of that tangent line and the derivative at the point where they touch are equal to each other. The notation that we use, there's several different notations that you'll see. A rate of change is a slope. Slope, remember, is a change in y over change in x, delta y over delta x. You actually will almost never see it written like this, though. For some reason, with derivative, instead of delta y with the triangles, you'll actually see it written as dy over dx way more often, dy dx. If we are using function notation, f of x notation, the derivative is written as f prime of x. Again, that's read f prime of x. It's f with a little apostrophe there. So suppose we need to find the slope at this point right here. We need to know what the derivative is at that one given point. We know it's positive, and we know it's not as positive as it was down here. And we know it's more positive than it is in here. And we could sketch in a tangent line and approximate what that is. It's a terrible line. But it looks like it's about 1 up 1 over 1. So you could approximate it. But in general, we want to know at any point what is the slope of that curve. We want an equation, an expression that's going to give us the derivative. So let's call this x value, I know it looks like on this graph it's x equals 2. This is just going to be a general x. And if I had a second point, we know how to find the slope in between 2 points. So let's pick a second point. Let's choose this point right here. And we're going to find the slope between those 2 points. Notice the slope between those 2 points. While it's not the same as the slope of the curve, it's at least somewhat a little bit close. So there's my second point. The distance between these points is going to be a change in x. That's a delta x. Let's call this function f of x. This x value, if it has an x, the y value would be f of x. And if I started at x and went up by delta x, this x value right here would be x plus delta x. So this y value is f of x plus delta x. So to find the slope in between these 2 points, we are going to do y2 minus y1. So the y value of this point minus the y value of that point. F of x plus delta x minus the y value of the other point, so minus f of x, divided by x2, so the x value of this point, minus the x value of this point. And notice right here, I've got x minus x. Those cancel, right? And notice we get the difference quotient. The difference quotient is the slope between any 2 points. Problem is, we didn't want the slope between those 2 points. We wanted the slope at this one point. So we want to think, how could I get a better representation of the slope at that one point? So here, that's not a great representation. But if I take this point right here, I erased the whole line, and I moved it closer, maybe it was like right there, notice that's closer to the slope of the tangent line. And if I took that point and I moved it even closer, now the slope between those points is even a closer representation of the slope of the tangent line. I can't make it so the 2 points are right on top of each other, but the closer and closer I move them, the better the representation would be. So I want delta x to be as small as possible. I want it to not be 0, because it can't be 0, but I want it to approach 0. So this is the limit definition of derivative. Whether you understand where that comes from or not, that's not terribly important. What is important is that you know what this is. This is the derivative of f of x. F prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. That will give us the derivative at any point on a curve. So example 1 asks us to find the derivative of f of x equals 2x squared plus 3x. F of x equals 2x squared plus 3x. So to find the derivative of a function, we want to evaluate the limit as delta x, or if you prefer to use h, goes to 0 of f of x plus h minus f of x all over h. You can use h or delta x, either one's fine. We've evaluated this given a problem like this. The only thing that's new is defining it and calling this the derivative. You need to know the formula now. You need to know this expression. But from this point forward, we've done all this stuff before. So you can go ahead and work through it as I am here on the board. And once you think you have your answer, hopefully I'll be done. So once we expand everything, we cancel out the things that cancel. We factor out an h. That h cancels with the 1 in the denominator. And then we plug 0 in for our h. Plugging 0 in for h gives me 4x plus 3. So the derivative of 2x squared plus 3x is 4x plus 3. Now let's take a look real quick on the calculator as far as what this means. So if I were to graph y equals 2x squared plus 3, get rid of these other graphs. Notice when x is -1, I'm going to change my window a little bit so we can see it a little bit better. Let's go from -3 to 3 on the x, and from -1 to 8 on the y. Oh, I missed my x there. That's what's going on. 2x squared plus 3x. Sorry. Y min -3, y max 8. All right, so notice when x is -2, I have a negative rate of change. My derivative's negative. Notice if I plug in -2 for my x here, I get -5. So at that point right there, the slope of the curve, if I were to sketch in a tangent line, would be about -5. At x equals -1, x equals -1, notice the slope's -1, so it's negative, but not as negative. At x equals 0, my slope is 3, and so on. So what this is I can plug any value in for x, and it's going to tell me what the slope of the curve is at that point. Notice if I were to find the minimum of this curve, calculate minimum, it's in between -2 and 0. My minimum's at -3/4. That point where it reaches the lowest point there is -3/4. If I plug in -3/4 for x, that gives me a slope of 0. The derivative is 0 at that lowest point. We were asked to find the derivative of each of these. I want you to do the derivative of x squared and x cubed in your notes. And I'm going to do the derivative of x to the 4th. You don't need to copy that into your notes at all. But I do want to take a look at what that looks like. You can actually pause the video and then when you're ready, resume it. So hopefully you've done the first two. This last one, notice I expanded. I factored out the h, canceled. When I plug in 0 for h, I get 4x cubed. So if f of x is x to the 4th, then the derivative is 4x cubed. You should have gotten for your derivatives here. This one is 3x squared, and the derivative of x squared is 2x. What I want you to do is think about if f of x is x to the 5th. Notice we don't always want to do it this way. If f of x is x to the 11th, this is going to be awful. But taking a look at these, we should be able to figure out what the derivative of this is. Notice the coefficients go 2, 3, 4, so this one's going to be 5, and the exponents go 1, 2, 3, so this one's going to be 4. What if it is f of x equals x to the 11th? That's what we're doing is we're taking this exponent, moving it out front, and subtracting 1 from the exponent. So the derivative would be 11x to the 10th. The 11 goes out front, we subtract 1 from the exponent. So to find the derivative, we could do it the long way. and sometimes you might have to. But a lot of times we can use what is called the power rule. The power rule is how to find the derivative of x to an exponent. The derivative of x to a number. X cannot be in the exponent here, but x to a number. We take that number, we move it out front, and we subtract 1 from the exponent. Example 3, I think it's actually example 2. We skipped example 2. Asks us to find the derivative of each function. G of x equals square root of x, which does not look like a power, but if you recall, square root is the same thing as the 1/2 power. So we should be able to use that power rule. Exponent goes out front. Subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. And you can leave it like that. It's fine to have negative exponents in your derivative. H of x equals 1 over x squared. First of all, you cannot just take the derivative of the bottom and say it's 1 over 2x. That is incorrect. Instead, we want to rewrite it kind of like we did here. This power rule only works if I have x to an exponent. So 1 over x squared, that's the same thing as x to the negative second. And now I can use the power rule. Negative 2 out front. Subtract 1 from the exponent. Since this was written with a denominator, we probably should over here as well. Negative 2 over x cubed. This one asks us to evaluate h prime of x, given h of x equals 5x to the 4th plus 6x squared plus 8x plus 3. If I have a coefficient, as long as it's just a number, it's just a coefficient, it doesn't have a variable in it, I can just take the derivative of the power part and multiply it times the coefficient. So the derivative of 5x to the 4th would be 5 times 4, subtract 1 from the exponent. 6 times 2, subtract 1 from the exponent. A couple different ways you could think about how to get the derivative of 8x. We could use the power rule. That's 8x to the 1st. So if I move the 1 out front, it would be 8x to the 0. And anything to the 0 is 1. So the derivative of that is 8. Another way you could think about it is, remember, derivative is slope, and 8x just has a slope of 8. 3, we could also do one of two ways. 3 is the same thing as 3x to the 0, which means I would do 3 times 0. X to the negative first. 0 times anything is 0. The derivative of any constant is 0. The slope of any constant is 0. Example 5 asks us to write an equation for the tangent line at x equals 3. So given f of x, we need to write an equation for a tangent line at a specific x value. So to write an equation of a line, we need two things. We always need a slope, and we need a point. Well, they gave us the x value of the point. So x is 3. To get the y value of the point, we just plugged in 3. So plugging in 3 gives me negative 18, negative 12, negative 9, I think. To get the slope of the tangent line, remember, is the same as the slope of the curve. The slope of the tangent line and the derivative are the same thing at the point. So to get the slope of the tangent line, we just need to take the derivative. We do it the same way we did this one up here. 3x squared minus 10x plus 2. 3 has a slope of 0. That's the slope of the curve. I want the slope at x equals 3, so now I can plug in 3 for my x. So the slope of the curve is -1. So I have a point and a slope. Now it's an algebra 1 problem. We know how to write an equation of a line. I would use point-slope form. And unless this is a crazy fraction, let's go ahead and change it to slope-intercept form. So y equals -1x minus 6. And that is going to do it for today. We're going to call it right there.